Adding letcc to curly means that we have a new letcc form that has a symbol that we bind the continuation to and a body expression. And we also need a new continuation value. We've got continuations with this cont data type that are continuations that the interpreter uses, but letcc needs to bind a variable to a value that is a continuation, so we need a cont_v wrapper to wrap a continuation as a value. And then we're going to make apply work with those continuation values. So the letcc case of expressions where we have a name and an expression is straightforward. We want to evaluate the body in an extended environment where we've bound the name to the current continuation. That is, k is the current continuation. It's the continuation of this letcc expression. We're converting it to a value, binding it to that name in the environment. When that name gets used, then a cont_v value will be found by lookup. And one of the place where that value could be useful is if you try to apply it to something. So we're in the continue function now. We're in do app k. So v is a value that we are passing to a continuation, and vf is a continuation. Well, it's either a closure or a continuation, but we're interested in the continuation case. So when the function position is actually a continuation, then it has a continuation inside of it, and that's the one we want to continue with. We just forget about the current continuation k, we use that kv instead, and pass it along the value that we got from the arguments. This is why I say continuations are easier to implement than know what to do with them, because just replacing the current continuation with one that you've saved is pretty straightforward. We can go look at the implementation where there are some new examples. This example produces 10, but it's an interesting one because it uses letcc. So what happens here is that when interp gets to this letcc expression, it saves the current continuation, which corresponds to let f be something, right? That's the expression we're waiting for, in f applied to lambda x10. So this expression is what gets bound, that's the current continuation, that gets captured and saved as k. And then we return k to f. So now f stands for this thing in blue, that saved continuation. And we apply f with this lambda. That means we call this continuation, we use it in place of the current continuation, and we take this argument lambda x10, and that goes in place of the dot. And now if we continue from this point, then we get a function back for f. We apply f to some other function, which goes in as x, but x is ignored, and we just return this 10 here. So that's how we get 10 out as a result. I have another example staged here. So here's a larger example where I'm letting escape be a continuation that is just something applied to 2. So the something is whatever is delivered to that continuation. And then I start letting v be add 1 to some other expression, but that other expression is going to escape. It's escaping passing k. So k at this point corresponds to, we had waiting outside something applied to 2, but inside of that we had a let v be plus 1, and that's where we are now. We're right there in that plus 1 where we captured the continuation, and then there's another lambda a plus va inside the body there. All of that waiting to be applied to 2. So we escape out, and this continuation is what we pass to receive the value 2. So that means the value 2 is going to go in here. And now we have v is 3, and then we return a function that's going to take an a and add 3 to that a. 2 comes in as the a, so that's why we're going to get 5 out as the result here. If this is a little mind-bending, that's okay. We're grabbing places in our computation and then jumping to it. Much like a goto, but even stronger than a goto, because it's going across what you normally think of as stack frames and jumping back into stack frames. So let's look at some examples of where this could actually be useful next.